Okay, so we look at electricity. We look at electricity with the subheading the electrical circuit. Okay, so we have to know how to calculate the circuits um, given in case you find such kind of questions in an exam under physics. It's always a must. A circuit has to be there. So we have electricity here. Okay, so our subheading that we are going to concentrate much on. It's the electrical circuit. The electrical circuit. Okay. So now, just to briefly define what electricity is, this is just the form of energy. The form of energy. Okay. I'll just write this. So electricity is the form of energy that powers devices, machines, and systems, which are essential to modern life. Okay, so it is generated, transmitted, or utilized in various forms, making it a versatile and widely used energy source. That's electricity. So it's just a form of energy, this one, and it can be um, the form of energy that powers electrical devices, machines, there are a lot. Yeah. So when you talk about now the electrical circuit, this one it's the path. When you talk about the electrical circuit, this one it's nothing but the path in which the electric current flows. So this one is nothing but the path in which the electric current flows, or others they will define this um, as a closed loop. So they can define electrical circuit as the closed loop that allows electric current to flow. So electric current to flow. So this closed loop, it's the one that we have to that's it's the closed loop. This closed loop is the one that we are going to concentrate much on. So the closed loop is something like this. It's closed, so it's just a loop. So this is what we are going to concentrate much on. Since now we've defined as in the electrical circuit being the path or the closed loop that allows electric current to flow. Now, what is the current? What is this current that is being talked about? Current here. So what is current? Current is nothing but the rate. Current is nothing but the rate of the flow of charge. Of the flow of charge. So this is the definition for current. So since we know the definition, current is being measured in amperes. The unit of current is called the amperes. Is called the amperes, being denoted as in A. Okay, so we have the definition, the unit, and yeah, the definition and the unit. So now, since we said that current is the rate of the flow of charge, the rate. So this rate here, it's time. It's time. The rate that is being talked about here, it is the time, and time is being measured in seconds. Okay, so apart from that, there is the flow of current, the rate of the flow of current, the rate of the flow of charge. So current is being defined as is being defined as the rate of the flow of charge. Now, what is this charge? Okay, so this charge here is being measured in what? In coulomb. So this is the unit of charge, coulomb. It's being denoted by C. So charge, the coulomb is being denoted by C, but charge is being denoted by Q, and current is being denoted by I. Okay, so we have this now. Since we know that current is the rate of the flow of charge, and its unit is called the amperes, which is being denoted by A, and coulomb being denoted by C, what formula can we use for us to calculate current if we've been given the rate, which is time, and the charge in coulomb? So this is the formula that we have to use. Current is equals to the charge over time taken. So this is the formula that we are supposed to be using. So now, since we know the formula that we are supposed to be using, the instrument used to measure the current, which is in amperes, is what we call the ammeter. This is where the A comes from, is what we call the ammeter. So this is the instrument that's used to measure what? To measure the current. So for example, if you've been given given a question like a stove, let me use a stove. A stove, okay. So a stove uses a current. A stove uses a current of, let me say, 5 amps. Even if it's yeah, a stove uses a current of 5 amps for 10 seconds. Okay, let me say for maybe for 2 seconds. For 2 seconds. So a stove uses a current of 5 amps for 2 seconds. How much charge? How much charge? How much charge flows through it? Flows through it. So how much charge flows through the same stove? So a stove uses a current of 5 amps for 2 seconds. How much charge flows through it? So we go back to our formula. This is our formula here. So what we can do is just get this formula. But in physics, when it comes in terms of calculation, not in physics only, but any course or subject that deals with calculations, the first step that we do is we start by correcting data. So we correct the data here, like what we've been given in the question. The question, in the question, we have the current and the rate. So the current here in the question is being given as in 5 amps, and the rate, which is time, is being given as 2 seconds. Then the question says, for how much, as in how much charge flows through it. The charge is the one that we have to calculate. So you go with the solution. Always collect data when you are dealing with calculations. Correct data, then the solution. So the solution, this is where now our formula comes in. So you have the charge over time taken. So current is equals to current we've been given. Current we've been given to be 5 amps. So we have our 5 amps here equals to the charge is the one that we have to calculate over the time, which is 2 seconds. So if you, over 1 here, you cross multiply. 1 times the charge you're going to have charge equals to, what is 5 times 2? That's 10. So we're going to have 10 coulomb. So the 10 coulomb, it's the one that flows through the stove. This one for the current of 5 amps and for the current of 5 amps running for 2 seconds. Okay, so this is what we are going to have here. Okay, so now since we've talked about the current, let's look at another parameter called the electromotive force. So the electromotive force, this one here, is the one that we have to talk about next. Let me just erase this. Okay, so I erase this. Then we talk about the electromotive force. Okay. I can just erase this as well. Okay, so now let's talk about the electromotive force. Since now we've talked about the current, the electromotive force, this one, it's been denoted electromotive force. So this is our F, sorry, electromotive force. So electromotive force. So this one forces whatever has to flow in the circuit. So the electromotive force, this one, of a battery or a cell. A battery, a cell, if you have maybe 2 or more cells, makes a battery. Makes a battery. Okay. So the cell is the one that forms, if you have 2 or more cells, forms a battery. So this one, the electromotive force is being defined. Let me use the black ink. Okay, let me use the black ink here. So the electromotive force is being defined as the energy. Since there's a force, since there's force here, energy has to be there. Because of this force, it makes the electromotive force to have what? To have energy. So energy, the electromotive force is being defined as the energy, the energy supplied, as the energy supplied to each coulomb, to each coulomb of charge within it, to each coulomb of charge within it, So this is your electromotive force. Because of that force, energy has to be there, because force, we cannot have, force without energy. So energy has to be there. Okay. So now, how do you calculate the electromotive force? If maybe we find a question that talks about calculating the electromotive force. So the electromotive force, this one, they say that they say that the one voltage is equals to 1 joule per coulomb. 1 voltage is equals to 1 joule per coulomb. So what does this imply? We can tabulate now. We can come up with the formula from this here. We can come up with the formula from this. So now the formula that we can have, electromotive force, which is EMF can be equal to the joule. This one, joule here, it's the energy, because energy is being measured in joules. Okay, so we're going to have the energy over the coulomb here is the charge. So this is the formula that you can use to do what? To calculate the electromotive force. So electromotive force is equal to energy over charge. Since 1 voltage is equal to 1 joule per coulomb, so electromotive force therefore is equal to energy over charge, whereby the electromotive force is being measured in volts, energy is being measured in joules, and the charge is being measured in coulomb. Okay, so since we've talked about the electromotive force, let's now go to the other parameter that has the voltage, that has the voltage, and that parameter is called the potential difference. So let's look at the potential difference, like what is being involved in the same potential difference, and how is it different from the electromotive force. Okay, they share the same unit here, but the definitions are different. Okay, so now here we have to talk about the potential difference. So the potential difference is being denoted as in PD. This is our potential difference. So now a potential difference of a cell or a battery is being defined. Let me say, let me not put the cell or the battery. Let me just say the potential energy. I mean the potential difference. This one also, it can be the energy. This one, since there was the it has to carry the energy by charge from a cell or a battery, which is being consumed in electrical components like the resistor, the lamps, whatever you can have. So in the potential difference, there is an energy actually which has to be there as well. But I never wanted to use the battery or the cell. I just wanted to go like direct to the definition. Okay, so the potential difference is defined as in the energy, is being defined as the energy converted per unit, the energy converted per unit charge, passing through it, passing through a component, So this is the definition of the potential difference, is the energy converted per unit charge passing through a component. But when it comes to the electromotive force, it's not the energy converted, but it is the energy that is being supplied. So when it comes to the electromotive force, this one, it's not the energy converted, but the energy being supplied. This one, it's being supplied. The energy has to be supplied. to each coulomb of charge. But when it comes to the potential difference, the energy has to be converted per unit charge passing through a component. Okay, so now since we have that, what can we have now? Since we know the definition, when it comes to physics, chemistry, when it comes to physics and chemistry, or let me just say courses or subjects that deals with calculations, the first thing that you have to know how to define what you've been given. Then the second one is you have to know its SI unit, like in how it's being measured. Then the third one, it's the formula. So define the definition, very much important. From the definition, the unity, the SI unity. From the SI unity, the formula. So once you just know this, the definition, the SI unit, and the formula, then you are good to go. As long as you're dealing with calculations, you are good to go. So now, since we've talked about the definition of the potential difference, let's look at the SI unit. Also, the potential difference is being measured in voltage. Okay. Also, the potential difference is being measured in volts. And the formula that we can use to calculate the potential difference, since there's energy there, since there is the energy being since there's the energy being converted per unit charge passing through a component, there's a charge as well there, so it's going to be the same. So the PD, which is the potential difference, has to be equal to, let me use the red. Okay, so we are going to have the PD equals to, we have the energy, you divide it by the charge there. So that one becomes your formula, whereby PD is being measured in volts, the energy is being measured in joules, and the charge being measured in coulomb. Okay, so the potential difference, the instrument that you can use to measure the potential difference is the voltmeter. Since it's been measured in volts, the voltmeter, that's the instrument we can use to measure volts, to measure the voltage. Okay, to measure the potential difference. Yeah. Okay, so now let's look at 2 or 3 examples so that we see like as in how far we've gone with understanding this subtopic, the electrical circuit. We have to start now looking at the circuits in general. Okay, so now let's try to look at the example. Let me just try to erase this, which is down here. Okay, we erase this one. So know the definition, the SI unit, and the formula, then you are good to go for you to solve chemistry or physics questions. Okay. Okay, we can proceed now. We can proceed. So here is the charge. I'll be using the stove. So we have, let me say, maybe I'm using the stove as an example. So we have example 1. Okay, so example 1, the question reads 25 coulomb of a charge, 25 coulomb of charge, 25 coulomb of charge flows through a stove. Okay, flows through a bulb. This one to be different. Yeah, flows through a bulb, which transfers which transfers 200 joules 200 joules of energy 200 joules of energy into light. What is the potential difference? What is the potential difference? Okay, the potential difference. So here is the formula. Here is the here is the question. So you have 25 coulomb of charge flows through a bulb, which transfers 200 joules of energy into light. What is the potential difference? Like what I said before, the first thing that you have to do is, I know what you've been given in your question. You first start by correcting data. Here we correct our data. So 25 coulomb of charge. So we have the charge here being given as in 25 coulomb. Flow through a bulb, which transfers 200 joules of energy. So energy here, we've been given that it is 200 joules. Okay, into light. What is the potential difference? Now, what is our PD? Our PD, we don't have, then you go to the solution here. As simple as this. So once you just know how to collect data, you can even know the formula that you are supposed to use. So now our PD here, PD is equals to energy over charge. Direct. Your PD here is equals to, what is our energy? Our energy, it was 200 joules over the charge, it was 25 coulomb. So PD is equals to, if you divide now that one, what is 200 divided by 25, you're going to have 8. So the PD here, we had 8, and voltage, because potential difference is being measured in volts. So this one becomes your answer. As simple as that. Let's try another question. Let's try another question, another example. Example 2. Example 2. Try example 2. Okay. I'll try to make a different question from you. The same. Example 2. Okay. Example 2. Okay, let's use black. Okay, so example 2. Okay, so now this one here, we have when a current when a current of 4 amps, when a current of 4 amps flows for 10 seconds, through a bulb, flows for 10 seconds through a bulb, 300 joules of energy are consumed. 300 joules of energy are consumed. 300 joules of energy are consumed. So now the first question is, how much charge flows through the bulb? How much charge flows through the bulb? Then the second question is, what is the potential difference across the bulb? What is the potential difference across the bulb? Okay, what is the potential difference across the bulb? So the usual thing, we go with our data. We have to collect data first. Then once collecting data, we go to the solution. Then everything is being sorted out. Okay, so now we collect what we've been given. So now here on the data, okay, so the question, when a current of 4 amps flows for 10 seconds, time we've been given that it is 10 seconds, through a bulb, 300 joules of energy 300 joules are consumed. How much charge flows through the bulb? How much charge? They want the charge, we don't have, and the PD here, and the PD, okay, we don't know. So solution A, the first one, we have to calculate the charge here. So how do you calculate the charge? You have current is equals to charge over time taken. Okay, current being given, we have 4 there, equals to charge, we don't know. The time being given, it is 10 seconds over 1. You cross multiply. So meaning your charge here is equals to, what is 4 times 10? That's a 40. So I have 40 coulomb. That's the answer for solution A. Then we go to solution B. So solution B, they want the PD. So the PD, as in the potential difference, is equals to the energy over the charge. Since charge we've calculated 2, we've calculated charge in solution A. We know the charge. So our PD here is equals to energy given, it is 300 joules. You divide it by 40 coulomb, which is the charge. So PD is equals to, you can cancel the zeros here. Okay, so now what is 30? You divide it by 4. You're going to have 7.5. So the voltage here, it was 7.5 volts. That was our PD. You are done with this question. So that's how we do some calculations. Okay. So now let's go to, we start now looking at the circuit, how the circuit behaves, some parameters involved in the circuit. Yes, so that we see as in how far we can go with the same calculations. Okay, so now for us to look at the calculations under the circuits, we have to know some parameters being involved there. Okay, so a circuit, it was being defined as in a closed loop through which the electric current flows. A closed loop. Okay, so if they say a closed loop, meaning it's supposed to have a leakage there. Okay, we did it with this one here. Okay, yeah, so use a black pen. Okay, so here is the circuit. So a circuit has to consist of a battery. It has to consist of a battery and being, yeah, I'll give you an example of what we had, what boys have been doing maybe by the age of 8, the age of 4, somewhere there. So we used to get the batteries, those cells. Okay, this is the battery. This is the battery. Then you find that the battery here on the top, it was indicated as in positive, here as in negative. Back then we never used to know to say where is the positive, where is the negative. We just used to connect. As long as the lights comes on, then that's it. We are okay. So you find that we used to connect it to the bulb here. This is the wire. The one leg of a bulb has to be connected to one, has to be connected to one end of the wire. So you find that the one leg of the bulb has to be connected to one end of the wire, and the other leg of the bulb has to be connected to the other end of the wire, being connected to the battery. Okay, so you find that if you find that if you just try to carry this experiment here, this bulb comes on. If you do this experiment, the bulb comes on. But if you try to disconnect here, let me use if you disconnect this here, the bulb goes off. So this connection here, this is where we never used to apply the method of having the switch. But this one, it was acting as a switch. Why? It's because if you connect it here, you find that the bulb has to be turned on. But if you disconnect this, the bulb goes off. Same applies to this one. If once you just touch the wire to the positive side, the bulb goes on. But if you reconnect this one, the bulb goes off. So this was the simple experiment we had. We never used to know to say where is the switch, where is the what. No, we just used to get the wire and the bulb and the battery. That's it. So now, to present this on a schematic diagram, we're going to have something like this. This is the cell. Okay, then just direct, then you connect something here, which is the bulb being connected here. Okay, that's it. So this one becomes the closed loop. Why? It's because the closed loop, once it touches here, you find that now current flows in this direction. It will flow, trying by means to turn on the bulb. So this is what we are going to be discussing on. So now, since we have this, before we start discussing about this one, let me let us look at this parameter called the resistor. We look at the parameter called the resistor, then we can start, because this one, it is important as well to understand its part, what it does to the electric circuit. Yes. Okay, so let's discuss about the resistance. the resistance. What is the resistance? Okay, the resistance. So according to just according to the weight, it resists, meaning it tries by all means to oppose the flow of current. So the resistance, this one is the opposition to the flow of current. Just the weight itself resist, meaning opposing. So now we have resistance as in the opposition to the flow of current, the opposition to the flow of current. So this is the definition of the resistor. Resistor has been measured in ohms, and this is how we denote the ohm. Okay, that's how we denote the ohm. So this is the ohm here. This is the ohm. This is how we denote it. Don't try to circle it. No, I was just trying to show you that this is how we denote the ohm. Okay, so from there, since we know the definition of the resistor, it's SI unit, and the next thing that we have to talk about is the formula, how we can calculate the resistor. We can use Ohm's law. I love this. Ohm's law, V equals to IR, meaning the voltage is equals to the voltage is direct proportion to the current and the resistance. The voltage is direct proportion to the current and the resistance. So we can use this one, Ohm's law. If you want to calculate for resistance, you make R the subject of the formula. So I and I goes, meaning R is equals to the voltage over the current. You can calculate your resistance using this one here. So this is the formula. Okay. So from the resistance here, we have what we call the device which provides some resistance in the circuit is called a resistor. We have a resistor. A device that provides some resistance in the circuit is what we call a resistor. And a resistor, it looks like this. It looks like this. Okay. Those ones who are going to choose to do engineering, these are the things I'm going to be dealing with here. Okay. So this is the resistor, and it has, you're going to find it with different bands. This here, yeah. We have something like this, and this one, let me try to add the tolerance. Okay, and the tolerance there. Okay, so this is how the resistor looks like. This is what you're going to be finding as in the resistor. This is how it looks like. So since we have something like this, how do you calculate the resistance? So there are two main ways. I mean, you can calculate the resistor if you've been given the voltage and the current using this formula for Ohm's law, or you can calculate the resistance using the color coding. Color coding. This one, when you start doing your those ones who are going to do engineering, this is how we calculate the resistance. Just looking at the colors of the resistor, you're able to tell to say this resistor, it's maybe 1000 ohms, maybe it's 100 ohms, or maybe it is 10 milli. I mean, yeah, it's what's this 10 mega ohms, or maybe it's 1k ohm. You are going to know through the colors. This is what we that's what we call the color coding. Okay, so let me give you an example of a question to calculate, not using the colors, but using the formula being given the potential difference, the voltage there, and the current. How do you calculate the resistance? Okay. How do you calculate the resistance being given those parameters? So this is what we are going to this is what we are going to discuss, how it has to be calculated. So we start. Okay, so here is the question. Let me just try to change to black. Okay, so here is the question. A current of 2 amps, let me say 4 amps, so that we are a current of 4 amps flows through a conductor, through a conductor the conductor has the potential difference. The conductor has the potential difference of 12 voltage. Let me say 10 V. Okay, the potential difference of 10 voltage. Find the resistance find the resistance, find the resistance of the conductor, of the conductor, of the conductor. Okay, so as yeah, we go to our usual thing with data first here. What have we been given in the question? A current of 4 amps. We have a current of 4 amps flows through a conductor. The conductor has the PD, the potential difference of 10 voltage. Find the resistance. We don't know. So solution here. So the solution, we go with the formula R equals to V over I, or V equals to IR. What is our R? We don't know. Then what is the PD? In volts, that's the 10 over what is the current? That's the 4 amps. So our resistor equals to, so if you divide what is 10, you divide it by 4, you are going to have a 2.5 ohms. You're done. So these are the questions you're going to be finding. They will try by all means, like they can even give you the resistor and the PD, then they tell you to calculate the current. You just use the same formula. Ohm's law, V equals to IR. This is the formula that you are supposed to be using if you've been given the resistor and the current, then they ask you to calculate the voltage, which is the PD. Or they can give you the PD, the potential difference, and the current. They ask you to calculate the resistance, which is this question here. Or you can be given the potential difference and the resistor, then they ask you to calculate the current. The same formula works. So there's nothing like maybe let me use the different formula. Okay, let me try to find the time. Let me try to find the charge. Let me just collect data first. The data that you collect is the one which is going to guide you the formula that you're supposed to use. As simple as that. Okay, so let's rush now to the symbol of the electrical component so that we start looking at the circuits now. The symbol of the electrical components, we start looking at the circuits. The symbols. Very much important to know the symbol because the electrical circuit comes with only the symbols. They won't be telling you to say this is the resistor, this is the rheostat, these are wires, this is junction connection or what. They're only going to be using the symbols, and you have to know them by heart. Okay, so the electrical symbols, let me try to erase this as well. So we have the electrical symbols now, so that we start looking at components. Okay, this one here, the electrical symbol components, it's a must. You have to know this before we start looking at the electrical circuit. We have this here, and there's a node here. So this one is, these are just connecting wires. Connecting wires. They are connecting. These are just connecting wires. But if you had something like this, there is a node here as well. These are wire junction. That's a junction there. This one here is the junction. Okay, then if you just have something like it doesn't have a node here, these are just crossing wires. Crossing wires. Okay, now what if you have something like this? This is what we call a switch, as we never used this when we were making those lights to be turned on. We're just using it direct there. You connect back to the battery. So this is the switch here. This is the switch. Then from the switch, you are going to be finding something like, I think you've seen what I drew maybe earlier on. I drew something like this. Okay, so this is the cell, and you know that a cell, this is a cell. So for it to become a battery, it's supposed to have more than 2 cells. It becomes a battery. And if you had something like this, more than 2 cells, this one becomes the battery now. Okay, so from there, the resistor, it's going to be presented like this. You're going to be finding a resistor like this one here. This is the resistor. Or others do be drawing like this. when it comes to the schematic drawing. You have something like this, that's the resistor. Then from the resistor, if you have a cross like this one here, this one becomes a rheostat. A rheostat. From there, we're going to have something. If you find something like this, I think this one I drew it as well. This is the bulb. Okay, then you find something like this. This is the ammeter, because there's that A inside. If you find something like this, just know this is the voltage. Just know that you have your voltage there. If you find something like this, there's a G there, just know that that's a galvanometer. Okay, so this is what we are going to be using for us to compose the circuit. We're going to be using these symbols here. There will be nothing like, no, this one. These are the symbols that we're supposed to be using for us to compose an electrical circuit. So let me erase this so that we can have a space. Excuse me. We can have a space here. Okay. We have a space for calculations. Okay. We have a space for calculations. Okay. So a circuit now, going to have something like, you have a circuit. Here's the battery. I think I drew this one before. So here is the battery, positive, negative. You have a battery there, then connected to the light. We draw this. This is what we used to draw back then. Okay, so you can present this. You have the cell there, and this is how you can present it. Negative. Okay, so this is how it can be presented. So let's talk about how we calculate this electrical circuit. These electrical circuits, you can calculate whatever parameter you've been given, knowing how it's been arranged. It can be either arranged in series or in parallel. It can either be arranged in series or in parallel. Okay, so we'll start first by looking at a series circuit. So we can start by looking first the series circuit. So a series circuit, the resistance have to follow each other. This is a series circuit. The resistors have to follow each other, being connected to a battery. Okay, being connected to a battery. So this is how it looks like if you have something in series. Okay, now since we have this in series, let's try to add, these are resistors, then this is the cell. So let's try to add some values. Let me say this one has been given maybe 4 and 5. Okay, 4 ohms and 5 ohms. Battery being given as in 30. The cell, this one, 30 V. So you have this one here. Now you have something like this. Okay, so since we have a circuit which looks like this, there are some of the principles that you have to follow if you are dealing with a circuit in series. Remember, you're dealing this one in series. So if you are dealing with a circuit in series, what happens to the current, the voltage, and the resistor? The voltage, the resistor together with the current that flows through that circuit. So we start with the current. So the current that flows through that circuit, once it is in series, just the same throughout. The total current is the same as in the current in the I1, current in I2. The current here, if this one is R1, the current R2. Okay, so the resistor of R1 and R2, I mean R2, R1 and R2, these are the resistors. So the current at R1 is equals to the current at R2 and is equals to the total current that is flowing through this circuit. Okay, this is the current. Now let's look at the electromotive force, which is that same cell. So the electromotive force is equals to, it keeps on growing. So it will be different from this point and this point to be different. Electromotive force at V1, we add it to the electromotive force at V2. I mean the voltage at V1, we add it to the voltage at V2 for us to come up with this total voltage here. So it keeps on going. If we had so many the resistors being involved, this is what we are going to be doing. Then for the resistor, for you to calculate the total resistor, you just add up R1 plus R2 plus it goes R3, R4, R5, it goes. So these are the principles that you're supposed to use, like more of the rules that has to be used on this. So now, since we know that current has to be the same throughout, let's try to calculate the resistor and we calculate the current. If now we've been asked to calculate the current which is going through this circuit, so the first thing that we have to do is we find the total resistance. So the total resistance is equals to, we add R1 plus R2. So R1, we've been given that it's 4 plus R2, that's 5. So 4 plus 5, we have 9 ohms. Okay. So now, since we have our 9 ohms, how do we calculate the current? Because the current is just the same. So we use Ohm's law. V equals to IR. So what is the voltage there? It's 30 equals to the current. It's the one that we have to calculate. You multiply by the resistor, which is 9. You divide it by 9. Also here by 9, you cancel. So meaning our current is equals to, so what is 30? What is 30? You divide it by 9. We're going to have the current of 3.33. It goes 3.33. Okay, amps. So this is the current that we have. So this current, it is the same at this resistor here at R1. It's the same at R2. But the voltages here, that are different. So how do you calculate these voltages? Ohm's law. Don't forget about this. So the Ohm's law of V is equals to IR. The voltage is the one that we have to calculate. V equals to, what is the current? We said that the current is the same throughout. So the current at R1, so we're going to have 3.33. You multiply by the voltage, I mean the resistor there have been given, which is 4. So if you multiply 3 by 3 times 4, you're going to have 3 by 3, you multiply it by 4, you're going to have 13.32. 13.32. So this one becomes your voltage at what? At V1. Then the voltage at V2, the same thing. The current 3 point, because it's just the same. 3.33 you multiply by the resistor being given there, it's 5. Okay. So if you multiply what is 3.33, you multiply by 5, you are going to have 16.65. 16.65. So if you add these two, they have to give you the total of 30 ohms. So plus 13.32. Yeah, it will be 29.9 21.97. If you round it off, it will be 30 because of these my points here. It was 3.3333, but as we just round it off to the to 2 decimal places. Okay, so these are the values of the voltages that you can have. So the voltage at this point here, the voltage at R1 here is 13.32 volts. The voltage at the potential, the electromotive force at R2 here is 16.65 volts. But the current is just the same throughout. So this is the circuit in series. Okay. So now let's look at the circuit in, if you've been asked to calculate the circuit that deals in parallel. How do you go about it? Okay, so this one is different from the circuit in parallel because the way we calculate in parallel, it's not the same way we calculate in a series. Okay, let me also erase the circuit. I erase the circuit. We look at the circuit in parallel. Okay, so the resistors have to be parallel to each other. That's what makes it the circuit to be parallel. The resistors have to be parallel to each other. So what I mean is, you're going to have a resistor here, then another resistor being drawn down here. If you have something like this, then there's a junction here being connected. There's a junction here, then it comes, just know that these two are in parallel. But if there was no junction here, these two becomes in series. Okay, I mean there's no node here. Okay, these two becomes in series. So I'll give you an example of this circuit here. You have a circuit. This is the resistor. Remember what we talked about this? That's the junction of wires there. There's a junction there of wires. Okay. Then being connected to the cell. Let me just try to, okay. So being connected to the cell. Okay, so we have this one. So this is in parallel. These resistors that are in parallel, they're not in series. They're not connected in series. Okay, so now since we have this, how do you calculate? So even this one, it has got the principles that you have to follow. Let me say the rules that they have to guide you. So when it comes to, we have the resistor here, the current flowing through, and the voltage. So when it comes to the resistor, for you to calculate RT, has to be 1 over R1 plus 1 over R2 plus 1 over R3 plus it goes. So this is how we calculate the one in series. I mean the one in parallel, or you can say RT is equals to R1, R2 if you've been given only two resistors. This is the formula that you can use, or you can use this one. RT is equals to R1, R2 over R1 plus R2. Okay, you can use either this one or this one. But when it comes to the current, you add the current. The current at R1 is not the same current at R2. It is different. So for you to calculate the total current, you have to add the current at R1 plus the current at R2. So to I1 plus I2 plus it goes I3, it goes. Then the voltage, when it comes to the voltage is just the same throughout. Remember when you are dealing with the series circuit, the voltage, it wasn't the same throughout. The one which is same throughout, it was the current. But now here in the parallel, the voltage, it's the one which is the same throughout. Okay, so now let's try to put some parameters. Let's use the same 4 and 5 here ohms, and the voltage, the same voltage of 30. Okay, so we have something like this. How do you calculate if they ask you to say calculate the voltage at this one is R1, this one is R1, and this one is R2. We have R1 here and R2. So for you to calculate the voltage at R1, so the voltage at R1 there, so the voltage at R1, which is V1, is equals to the same as in the supplied voltage, which is 30 volts. Same applies to R2. So V2 is equals to the same as in 30 volts. But the current at this point and the current at this point, they are different. So how do you calculate the current at this point and the current at this point? So let's try to find the total current flowing through this circuit. How can you calculate the total current flowing through this circuit? We have to know the resistor, the total resistor. So the total resistor RT, me I like using this one, R1, R2 over R1 plus R2, because I only have two resistors. And this formula can only work if you've been given only two resistors in parallel. So RT, the total resistor, is equals to, the total resistance is equals to 4 by 5 over 4 plus 5. So 4 by 5, that's a 20 over 4 plus 5, that's 9. So now what is 20? You divide it by 9. You're going to have 2.222, it goes 2.22 ohms. So this is what you're going to have. Okay. So you're going to have something like this, 2.22 ohms. So now since we have this one as in your total resistor, how do you calculate now the current? V equals to IR. Don't forget about Ohm's law. So the Ohm's law is the one that guides us as in how we are supposed to be calculating. If the circuit is in parallel or it's in series, you just use the Ohm's law. This one, if you've been given the resistor and the current, then ask you to calculate the voltage, use Ohm's law. If you've been given the resistor and the voltage, they ask you to calculate the current, same, the Ohm's law works. So now the voltage, the total voltage there, we say that the voltage is just the same throughout, which is V, which is 30 V there, equals to the current. It is the one that we have to calculate multiplied by the resistor, which is 3.22. Okay, this is our total resistor. So we have to find first the total current in that circuit. So I times 3.22, that's 3.22. So 3.22, for us to remain with our current here, we divide throughout by 3.22, also here by 3.22. So you cancel. So meaning your current, the total current here is equal to 30. 30 you divide it by 3.22. You are going to have 9.32. 9.32 being the current that is supplied um, in this circuit here. So you have the current of 9.32 being supplied across this circuit here. What will be the current at this point, and what will be the current at this point? So the current at this point here won't be the same current at this point. So because of this resistor here, what will be the current at R1? So the current at R1 will be equals to IR. The voltage there, we say that the voltage is just the same throughout, which is 30, equals to the current there is the one that we have to find. You multiply by the resistor of 4. So you divide over 4, also here over 4. Current is equals to, what is 30 divided by 4? What is 30? You divide it by 4. You have 7.5. We try to prove something here. 7.5 amps. Let's try the current at this point here. So we have 30 equals to the current at this point here to be I5 over, yeah, it will be I5. So you divide over 5, also here over 5. You cancel. So meaning your current there, it will be, what is 30 you divided by 5? 30 divided by 5, that's a 6. So you have 6. So if you add, that is 7.5 plus 6, you have 13.5. And if you calculate it like this, 13.5, this one becomes the total current. Why? It's because the formula that you've used here, they were supposed, you just went direct, like in using the ohms law, not knowing the current. We know the current that has been supplied, because the current that has been supplied to this circuit here, it's calculated, we calculated it to be 9.32. So 9.32, it was the current that was supplied here. 9.32, the current. So 9.32 is the current which was going through this node here. So now the 9.32 it's going to distribute across this resistor here and this resistor here. So if you can have this current here, let me just try to erase something here. Then we try to calculate nicely. We see the current which was being supplied at 4 ohms and at 5 ohms. Okay. So if you use the ohms law going direct, you just say no, there's a voltage there, because the voltage is the same. The voltage is the same, and I've been given the resistor. I can calculate the current there, and I can calculate the current here. What if you use the total resistor? You calculate the total resistor, then that's when now you start solving. It will go the other way, not the way we expected it to be. Okay. So there's a 30 here. We calculated everything. There's a 30 there. The voltage V is equals to, so IR 3.22, the resistance. So the current came out to be 9.32. Okay. So that was the total current that we are supposed to be using, 9.32. So now, since 9.32 it was the current, we have something like this. Total current here, it is 9.32 amps. Okay, so now we have the resistor here being connected to this node here, the current of 9.32 being supplied. Okay, then we have another here. Okay, so we have this current. So we have the resistor here of 4 and 5. So we can, here you can use, there's what we call the Kirchhoff's current law, and the Kirchhoff's current law, and yeah, which is the current divider rule and the voltage divider rule. So those are the ones that we are supposed to use for us to calculate the current at those different levels. It's just simple. For the current divider rule and the for the current divide the rule and the voltage divide the rule. It's just simple and straightforward. So this is the current that you've been given. So the current divide the rule, it says that the current, for us to calculate what's this? For us to calculate this one, the current here, I1. So to be the current I1 is equals to the resistor at R2 here, the resistor at R2, you multiply by the current, the total current. This is the total current. You divide everything by R1 plus R2. So you find that using this formula, here, current divider rule, you calculate the current at that point here. The current here, you find out the current here. So it will be the current I1 equals to the resistance R2, that's a 5, you multiply by the total current, which is 9.32, over the resistor, we have 4 plus 5. Okay, so now if you multiply what is 5 by 9.32, you are going to have 46.6. We are going to have 46.6. You divide this one by 4 plus 5, that's 9. So if you divide this one, it's 46.6 divided by 9, you are going to have 5.17. So 5.18 amps. That's the current at here, the current at I1. So we're going to have 5.18 amps. What about at this point here? The same formula, we just switch the values. So it will be I2 is equals to R1, the current, total current, over R1 plus R2. Okay, so our I2, because if we add those two currents, has to give us the 9.32. I2 is equals to R1, the R1 resistor, it's 4. So I2 is equals to 4, you multiply by the total the total current, which is 9.32, over 4 plus 5. Okay, so now if you multiply what is 4 by 9.32, you're going to have 37.28. So if you divide this by 9, 37.28, you divide it by 9, you're going to have 4.14 amps. So if you add 4.14 amps and 5.18, you are going to have the current of 9.32. So if you add 4.14 plus 5.18, you're going to have the current of 9.32 amps. This is the total current. So this is how you calculate when it comes to the circuit in parallel. So you know to say, from here, what am I supposed to do? Am I supposed to go direct? If you just go direct, you're going to find different values. Why? It's because this one is not in series, just for you to go direct with the Ohm's law, but it requires for you to think to say, what am I supposed to do once I reach this stage? So that's the good part of understanding the topic minus mastering it. If you just master, you'll be like, yeah, this is what I'm going to do, and you'll be calculating wrong things instead of you calculating using the right formulas and the right method. Okay, so now let's look at the electrical power, how we calculate the electrical power, and the powers, those units you do buy under Z-score, and how you convert those same units, and how those same units can be known through these same calculations we're going to perform. Okay, so let me just try to erase this part here. Okay, so this one will be our last part, the electrical power. Electrical power. Okay, so now the electrical power is being defined as the rate of using electrical energy. So this one is nothing but the rate of using electrical energy. Electrical energy. Okay, so the rate of using electrical energy is what we call the electrical power. So the unit of the electrical power is watt, being denoted as in W. Okay, so let's look at this. Then what formula can we use? Since we have the rate of using we have the rate of the rate and the energy there. So we have this one is being measured in watt. So power can be calculated as in voltage times current. Can use this one, or power is equals to I squared R, R squared I. Yeah, this. So all these are the formulas, but we'll focus on this one because here now there's no resistor which is being included. So we can just use this one here. Okay, so an example that I'll give you is let me just try to erase this one so that we look at the example. Okay, we look at the example. Okay, so now a bulb, this is the example, um, a bulb of 100 watts, a bulb of 100 watts converts 70 joules of electrical energy, 70 joules of electrical energy, 70 joules of electrical energy into light, into light and heat energy, into light and heat per second. So a bulb of 100 watts converts 70 joules of electrical energy into light and heat per second. So now per second. So now you have this one here. So now how can you, since you have a bulb of 100 watts that converts 70 joules of electrical energy into light and heat per second. So you have something like this bulb here. It will try by means to convert that energy of 70 joules of electricity. All the conversions has to be done in that given second. So you're going to have power is equal, if you have to collect data, for example, you want to calculate maybe something like, if you have to collect data here, what you've been given, um, oh sorry. Okay, here you've been given, you have the power, which is being measured in watts, you have the energy being measured in joules, and you have time, which is being measured in what? In seconds. So now power can be equal to energy over time taken. You can use this formula, and energy, you can use this formula to calculate power. It works according to what you've been given there. Power is equal to energy over time taken. You can use this one here. So since we know that this is the formula that we can use under power, or power is equal to voltage multiplied by the current, even this one works. Since now we know the formulas that we can use, let's try to look at this example. Let's try to look at this example. We see what we can solve from this. Okay, so now since we have this, let's try to erase this. Okay, let me use the bracket. Okay, so now here is the question. 20 voltage battery. The 20 voltage battery is giving, the 20 voltage battery is giving off a current, of 5 amps, is giving off a current of 5 amps to a resistor, Okay, find the power find the power dissipated, find the power dissipated in the resistor, okay. So as the usual thing, the first thing that we have to do is we start first by collecting data. We collect the data here. We've been given the 20 voltage battery here, so we have the voltage being given as in 20. We have the current being given there as in 5 amps, and we want to calculate power. We don't know, so we go to the solution. That formula, we have power is equals to VI. Power is equals to the voltage given there, it is 20 multiplied by the current, which is 5. So 20 by 5, 20 by 5, you're going to have 100 watts. Remember that power is being measured in watts, so you have that. Okay, so we go to the next one. What if you've been given the power, then they ask you to calculate the energy. I mean, you've been given the power, then they ask you to calculate the voltage. You still use this same formula. You've been given the power and the current, then they ask you to calculate the voltage. You still use this formula here. Okay, let's look at the cost of electrical energy. The cost of electrical energy. You buy the units under ZESCO maybe at 100 kwacha. How much units are you supposed to be given by the ZESCO? You buy the units at 100 kwacha, then you don't even know how much units you're supposed to get from that same 100 kwacha. So this is what we are going to be doing. Okay, so now when it comes to the cost of electrical energy, cost of electrical energy, okay. So when you use the electricity supplied by the ZESCO, you have the electricity meter, the meter there. So in the meter, you can find the unit of the kilowatts hour, meaning there's the watts there, which is power, and time. Okay, so this is what you're going to find in your meter box. I mean, the electricity meter. So you're going to have this one here, the unit, as in the kilowatts hour. So you have the watts there, which is in power, and the hour there being denoted as in time. So since we have that, by using this unit, the cost of electrical energy is calculated as in 1 kilowatt hour is called 1 unit. So the 1 kilowatt hour is called 1 unit. So now how do you calculate the cost of energy? Don't forget about the formula. Energy is equals to power times time, because here they're saying that if you just look at the electricity meter, inside there is what this unit is going to be there, the kilowatt hour. Then this watt here is being measured in this watt here is the SI unit of power, and the hour here is the SI unit of time. Okay, so now time here is not measured anymore. We're not going to be using seconds, because seconds are too like minimum. So we're going to be using something which has value like the hour. So this H here is the one that is going to be represented. This H here is the one which is going to be representing the time. So energy, the electrical energy can be calculated as in power times the time, power in watts and time in hours. So you have this. Okay, so the energy here, it's in kilowatts hour. The power here, it's in kilowatts. Then the time here, it is in hours. Okay, so now if the question comes like calculate the cost of electrical energy by you calculate the cost of electrical energy by if you've been given, let me just try to erase this part. We look at this question here. Don't forget about the formulas. Okay, so now here is the question. If electrical energy if electrical energy costs 50 kwacha. Okay, let me say 100 kwacha. It costs 100 kwacha per unit. It costs 100 kwacha per unit. What is the total cost by using 1000 kilowatts? So if electrical energy costs 100 kwacha per unit, what will be the cost? What will be the cost of using 500 units? Okay, what will be the cost of using 500 kilowatts hour? So don't forget about, let's first start by collecting the data. You've been given the units there. You have 1 unit is equals to 1 kilowatt hour. Then 500 kilowatt hour. So how many units there? We don't know. We have 500 kilowatt hour. Okay, so this one is just direct there, the solution. Then what we can do is cross multiply. So from here, x is equals to 500 kilowatt hour, because this is what we want to know now. Like, what will be the cost of 500 kilowatt hour? We want now the money here. Okay, so if electrical energy costs 100 kwacha per unit, then what will be the cost of 500 kilowatt hour? So one unit is equals to 100 kwacha. Now, how many units? What about 500 units? Because 1 unit is equals to 1 kilowatt hour. 500 units is equals to, we don't know. Then we cross multiply. So it will be 1x unit is equals to, what is 500 times 100? We are going to have 5,000. Okay, we're going to have 5,000. We're going to have 5,000 kwacha. So we're going to have a 5,000 kwacha. Okay, 5,000 kwacha is the unit that we're going to have here, the 5,000 kwacha. Okay, so 5,000, 1 2 5,000, yeah. So we're going to have 50,000, so not 5,000 but 50,000 kwacha. Yeah, so 50,000 kwacha is the one that you can use 500 units. So just do a cross multiplication. So 50,000 kwacha is the one that you are going to use for 500 units. So 500 units is equals to, 500 kilowatts hour. For you to use 500 kilowatts hour, you need 50,000. Okay, for you to use just a unit, you need 100 kwacha. Then now for you to use 500 kilowatts hour, just multiply 500 times 100. So 500 times 100, if you multiply, that's 50,000. So that's how you calculate. Just do the cross multiplication. Okay, so now let's look at this one here. Now this one, now they specify the electrical appliances that you are using in your house. So you have maybe the stove, the fridge, the bulbs, and the stove, the fridge, the bulbs, and the TV. You have to know the power that all these electrical appliances are using. So now let's look at this. A light, oh, okay, use a black pen. So a light bulb of 100 watts. A light bulb of 100 watts is used for 7 hours. For 7 hours. So what is the energy? So what is the energy? What is the energy cost if the energy costs 50 kwacha per unit? Okay, so it costs 50 kwacha per unit. So we have a light bulb of 100 watts is used for 7 hours. What is the energy cost if the energy costs 50 kwacha per unit? So the first thing that we have to do is we solve um, we solve the electrical energy for the light bulb. So how do you solve this one? The electrical energy, or the electrical energy for the light bulb. So electrical energy is equals to power multiplied by time. So this, let's first start by collecting data. Okay, so what we've been given in our question. So the data here of what we've been given in our question, we have the power of 100 watts and the time of 7 hours. Okay, the time of 7 hours. Then we want to calculate energy we don't know, so we go to the solution here. Okay, so the solution, we have energy is equals to power multiplied by time. So energy is equals to, what is the power? It is 100 watts. You multiply by time of 7 hours. So energy is equals to 100 times 7, that's 700 watt hour. Then you remember, we said that 1 unit is equals to 1 unit is equals to 1 kilowatt hour. 1 unit is equals to 1 kilowatts hour. So this one we have the energy here, it's just 700 watt hour. So 700 watt hour, we divide it by 1000 for us to get the kilowatt, for us to get the kilo. So we are going to have energy is equals to, now if you divide that is 700, you divide it by 1000, you're going to have something like we're going to have something like 0.7. So we're going to have something like 0.7 kilowatt hour. So the 0.7 kilowatt hour, this one here, it was the energy of the light bulb. Now the question proceeds to say, if the energy costs 50 kwacha per unit, what is the energy cost? So now 1 unit is equals to 50 kwacha. 1 unit is equals to 50 kwacha. What of 0.7 units? We don't know. Then you just do the cross multiplication. So meaning the energy, the energy cost, here, it will be the energy cost here in kwacha, it will be what is 50? What is 50? You multiply by 0.7. You're going to have a 35 kwacha here. Okay, so this is the 35 kwacha. So what is the energy cost if the energy costs 50 kwacha per unit? So it will be the 37, it will be 35 kwacha. So 35 kwacha is the one which has to make this light bulb works, because this light bulb, it contains 100 watts. It contains 100 watts, and it has been used for 7 hours. So since this bulb here, it contains the 100 watts and it can be used for 7 hours, meaning the amount of money you're going to spend on this for you to buy the units is just 35 kwacha. So this is how we calculate when it comes to electrical energy. I think we can end from here. Thank you.